to another edition of our thermodynamics series. Today we will be talking about a specific counter-rotating cycle that's particularly close to my heart because I worked in that industry for some time before coming to Cal Poly. It's the type of refrigeration system that's used in aircraft applications. It's called the Reversed Brayton Cycle, also called the air cycle machine. That gives you a hint that the working fluid or system in that particular cycle is going to be air, and why it makes sense to use it in an airplane application. So I hope that you enjoyed this video, and I look forward to hearing your comments on it. Take care. All right, to motivate or interest in developing this cycle, let's look at some of the unique requirements of airplane refrigeration or airplane air conditioning systems. Consider this beautiful little airplane here that's taken off, and let's just say that it's flying in what the industry calls a standard Army day. This establishes a set of heat loads on various components that therefore establishes a set of requirements that a refrigeration system has to meet. In that particular case, we're dealing with an airplane flying at 600 miles an hour in an ambient temperature that's 100 degrees Fahrenheit. So that's pretty much an extreme case for what an airplane might experience, right? To fly at 600 miles an hour, it would have to be at very low altitude. To fly at 100 degrees Fahrenheit, it would have to be at very low altitude. And in that case, it's rare that airplanes are flying at such high speeds. But nevertheless, it's a case to consider. And if that were the case, that corresponds to that airplane flying at a Mach number of 0.75. So almost at the speed of sound, 3/4 of the way there. And if you remember from your Fluids 2 class, that corresponds to a significant Ram effect, which itself increases the temperature of the air as it impacts the fuselage and any entry point into the system, which of course is what we're going to have to do if we're going to use the air as our working fluids here. And so that by the time you've stopped that air that's coming at you at Mach 0.76, its effective temperature goes back to its stagnation point, which is around 165 F. So we're going to be using air at 165 F to cool down the cabin. So that's going to be quite a challenge, right? So that's one of the major challenge that this industry faces. Also, there are other important heating loads here that are somewhat unique to the aerospace environment. The solar load, because this long fuselage is naturally exposed to the sun in all points of operation, is quite significant. Remember, the sun solar load is on the order of 1 kilowatt per meter square. That's a lot of heat per square meters, and a lot of surface on the airplane as well. So you see where that's coming from. And also, last but not least, the passengers inside the cabin are actually contributing significantly to the heat load inside the cabin too. So to deal with all these factors we're going to need a fairly significant source of refrigeration. And it's not clear yet that we're using air as a working fluid. In fact, we haven't talked about this yet, so you don't know this at this point in the presentation. That's what we're going to be using. But that is, in fact, what we'll end up doing in many cases. Could we use SVCC? It says SVSS here. I don't know why. Let's change that to SVCC. SVCC. All right, fixed. Of course, we could use SVCC, but is there an alternative to the cycle? And the answer is yes, you've guessed it. That's going to be the Reversed Brayton Cycle, what we're talking about today, which uses that air as the system for the refrigeration. So let's start by contrasting the SVCC with the Rankine cycle itself. That's a good starting point. Why? Because they are, in fact, the very same cycle, SVCC and Rankine cycle. As you recall, one of them is running clockwise and the other one is running counterclockwise. In the case of the Rankine cycle, of course, we're running clockwise because we're producing power, and so the net effect is work dot out net is greater than 0. And in the case of the SVCC, which of course, the expansion turbine here is really an expansion a throttling valve, expansion valve, so that it doesn't quite look like the Rankine power cycle in that respect. But we could make it look this way if we replaced that expansion valve with a turbine. And the parallels are obvious, I think. Because we're running counterclockwise, there is more heat coming into the cycle than there is. There's more heat leaving the cycle than there is heat going in, which means that we have a net work out that is negative in that particular case, right? So this guy here is work in, and it's clearly positive, and so that means that our net work out is less than 0. And so, yeah, as we expected, a refrigeration cycle must require energy to keep going. So let's open up the second law. So the point of this presentation, of showing these two cycles here, is that there is clearly a parallel between a power cycle and a refrigeration cycle. So we've also spent some time talking about the gas turbine Brayton cycle, and that's going to be our motivation for considering the reversed Brayton cycle. And it makes particular sense in the aerospace application, because the airplane itself is already working on the Brayton cycle to propel itself. So is there a way that we can kind of combine sort of synergically the fact that we're using a gas turbine to produce a refrigeration effect inside that airplane? And the answer is yes, there is. And that's what we're going to talk about. So let's look first at the Brayton cycle. Again, I've got my little triangles here that represent the compressor and turbine components of the gas turbine. So recall that the air initially comes in to the compressor. It's compressed to a state 2. Okay, at a point where the isobars from the low pressure P1 to the high pressure P2 are somewhat close together, meaning that the amount of work that's required, while certainly not insignificant, is much less than it's going to be further on when we move to the right on the TS diagram. We added heat between 2 and 3, and then we used this divergence of the isobars to produce a large, comparatively, compared to what went in, power workout, so that we had a net workout. Which, as we saw in our analysis of the Brayton cycle, based on our analysis of the entire cycle from the first law, the net workout is equal to the net heat in. Oops, that's correct here, right? Let's fix this. In minus out. And that's going to be equal to, the hatched area underneath the TS diagram that we've got over there. Okay. So that's a positive workout that we've got. So in the case of the reversed Brayton cycle, which is then motivated by this whole thing, we are going to go counterclockwise, right? And in that particular case now, the heat in that we've got, the green hatched part on this diagram, is much less than the heat out that's being dumped outside. Now the heat in that's coming in, that's the refrigerating effect that we're trying to do. We're trying to suck heat out of the aircraft cabin, and that's the area between 4 and 1 on that TS diagram, and that's a useful refrigerating effect. But it entails dumping out more heat, meaning that Q in minus Q out is now a negative number. And that's going to mean that work out minus work in is also negative, and therefore this cycle requires energy to function. Not surprisingly, it's a refrigeration cycle, right? So where does this energy come from is the next question. Well, in practice, it comes from those engines that are bolted onto the airplane already. So what we're going to do in practice, since we know that in the expansion of the turbine, and I have a nice little sketch here of what the system looks like here. In the expansion of the turbine, that's going to cool the air from 3 to 4. This is where the cooling effect takes place. And notice that we can't run this guy here like we did on the refrigeration, SVCC refrigeration cycle. In other words, simply throttle it back down, because the entropy increase would be such that by the time we end up at the pressure that we want, the temperature would actually be significantly higher than what we want here. That's what we would lose if we were to run this thing with a valve instead of using a turbine. So the whole point of this thing is to extract thermal energy from the air, and that's exactly what the turbine is doing, the cooling turbine is doing. It's not to produce power as much as it is to produce a cooling effect. So the cooling turbine is key here for doing that and get us as low a 0.4 as possible, where we're going to dump this into the cabin. So where does the energy come from to do this, right? Given that work out right here, which I had before, is clearly less than work in, which I require to run this cycle in the first place. And as I mentioned, that work is going to come from the gas turbine engine. So I'm going to take that gas turbine engine, which is, let's say, over here again. Gas turbine engine. This guy is running on the positive Brayton cycle, the one that you're used to. Compressor, turbine. All right, and I've got air coming in from 1 to 2, going into a combustor. Exactly the same diagram that I had before. Not before. And so what we'll do here, let's make that really clear, this is not a refrigeration cycle, this is a gas turbine cycle, the gas turbine itself. So what we're going to do is we're going to take some of that air that comes into the turbine, we're going to tap it out at some intermediate stage within the turbine, and that's what we're going to use to actually go into the initial compressor. So the diagram that I have here is an idealized representation of a closed cycle doing this. But in practice, we don't have this heat exchanger on the cool side here. We're simply taking air coming in from the gas turbine engine, and that is what is my effective state 1 for the air cycle machine. Right? So very similar to the Brayton cycle, which we could run theoretically in a closed cycle fashion, but in practice we don't do this. We take air from the outside and we dump it as exhaust. Here, in the case of the reversed Brayton cycle, in a similar way, we take air from the gas turbine engine at a suitable pressure, and we dump the outlet of the expansion turbine into the cabin, and that's our cooling. That's our cooling air. Okay. And so back on the TS diagram, this is where the air would come in from the engine compressor. So this is, let me call this maybe my 1 prime point here at this point, so that this distance between this intermediate isobar and my high pressure point of my air cycle machine is exactly equal to what I had on the left hand side through my expansion turbine, which is this guy right there. Deeper color here. There we go. So this guy is equal to this guy now. Boom, 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 boom. So those two changes in energy corresponding to the delta T between P int and P high are equal, and so therefore, voila, my cycle is balanced. But I had to pay for it, right? I had to pay for this increase in energy, which I sucked out of the gas turbine engine, and therefore that is fluid that is no longer available to propel the airplane. In the case of the aerospace application, however, that's a very convenient trade-off. In other applications, it's less clear. So I hope that we have a good understanding now of the nuts and bolts of the functioning of that particular cycle. what does that look like in terms of coefficient of performance? Let's take a look. As usual, as for any cycle, the coefficient of performance is defined as the useful refrigerating effect divided by the net energy input onto the cycle. And on a rate basis, that's the rate of cooling of the air divided by the net work into the cycle. The net work into the cycle is going to be whatever, and by the way, the net work in, as we define it here, is going to be based on the energy coming in at the original state 1, right? Because we've got to pay for that energy at some point as well. So we're going to account for that energy. So we're not counting the amount of the difference in energy between 1' and 4, so 1' and 2 versus 3 and 4, because of course, as I mentioned before, those two delta T's are equal. So we're going from the original air that went to the gas turbine in the first place all the way up to high pressure isobar of our air cycle system. So that means that it's the total work required to run the compressor from the very beginning minus the work required, minus the work that's delivered by the turbine to cool the system. And on the numerator is the heat that's being sucked out of the cabin as a result of that, which is going to be the difference between 4 and 1. Okay. All right. So applying the first law for these guys, and in this particular case, I kept work compressor minus work turbine, but I could have used first law analysis as well separately, right, from first law. As we've done previously, I could have said that work compressor minus work turbine, again, those are rates, they're not strictly work, it's more like power, that is equal to Q dot out minus Q dot in. Remember that out here is higher than in. And so work of the compressor, everything is the same mass flow rate, so we're going to use m dot for that. The total work done through the compressor is going to be, as we've got over here, H2 minus H1 from our first law analysis. Same m dot through the turbine, which is now H3 minus H4. Whereas if I'm looking at the heat being rejected minus the heat being added in, going back to our diagram here, Q out minus Q in. So Q out takes place between 2 and 3, and Q in, which in the ideal representation takes place between 4 and 1. That would be my Q in. So I'm looking at Q in is going to be m dot H1 minus H4, and Q out is going to be m dot H2 minus H3. M dot H2 minus H3 minus Q in, which is m dot H1 minus H4. Okay. The m dots are all canceling. And on that side, I get H2 minus H1, rearranging these guys, right? Minus, what do I have here? H3 minus H4. I've just rearranged this guy right there, and lo and behold, that's what I got on my left-hand side as well after I get rid of my m dot. And that just verifies our previous method, which is instead of computing the work in minus the work out, was to simply look at the heat out minus the heat in. That's what we did in the SVCC analysis, as you recall. But point here is that they're both the same, as you'd expect. All right, so that's what that expression here is over here. Removing the m dot gives us our final result for the COP of the reverse Brayton cycle. It's worth highlighting that one again. Let's just do that. Boom, COP. So the difference in enthalpies, between the air that's coming in minus the air that's going out into the cabin, if you will, divided by the change in enthalpies across the compressors and the turbine, respectively. Okay. All right. So this is good if we're going to be modeling the air as a real gas, but given that the CPs don't change very much within the cycle, it is often just as acceptable to model the air, the refrigerant air, as a perfect gas with constant CPs, and so therefore we can simply model the enthalpy as a product of CP times T, where CP is constant, which means that the COP, the coefficient of performance, simplifies significantly. Right, I've got some CPs here, which I've already removed for us. We use a different color here so it contrasts better. So let's just use red again so I can remove it easily. CP, CP's here, CP's there. All the CP's are going to cancel, which is why I had done that. And I've rearranged the temperatures on that side to factor out the T1 minus T4 in the numerator. And I get this nice final result in terms of temperature. Put a nice straight line here and box that one up too, because this gives us the final COP for a perfect gas in terms of the important temperatures in the cycle. Voila. Put that one back in there like before. Okay, so those are our two relationships for COP, whether we want to model them as ideal gas or as real gas, and that's it really. That's the end of the story for the reverse Brayton cycle as far as we're concerned. There's lots of super cool analyses that we can do with this, and when I worked in that industry, it was a really fascinating fascinating time in my life. I learned a lot about thermodynamics working there. To give you a taste of what some of the problems that engineers might have to face using this, consider the fact that as you go from 3 to 4, you might dip to at very low levels, right? If you're trying to get a maximum refrigeration effect inside a cabin, you want 0.4 to be as low as possible. Well, what's going to happen if you drop 0.4 below the dew point of air? And we're going to talk about dew point in the coming weeks. But what that means is the temperature at which the water starts to condense. And you know this, right? Dew on the grass in the morning on a humid night is significant, and that's because the grass and the ground is colder than what the air can sustain locally as a water vapor. So the same is going to happen in the turbine, the cooling turbine, and you're going to be spewing water out of that side of it. If you go even lower than 32, then of course you could be spewing ice and snow. So mitigating these effects is a real important aspect of the engineering of these machines. It's a really cool one. So starting to understand the relationship between humidity and air is very, very important. Very important part of this analysis, as well as the actual shaping of each of the components there in real life, as you imagine, just like we talked in the Brayton cycle. These components here are not ideal, meaning that they're not straight lines. They're going to be they're going to have isentropic efficiencies, which is not unity, and so therefore my cycle is actually going to lean over to the right continuously on both sides, and that's going to cost me. That's going to cost me on COP and ultimately on the amount of air I need to bleed out of the main engine. Always a bad thing. So what are the advantages? Well, there's many of them. The fact that the system is now simplified compared to what it would be for an equivalent system, compared to an equivalent SVCC system, right? I just have a compressor and a turbine. It's almost like a turbocharger, if you will, with a heat exchanger on top. The working fluid, my refrigerant, is completely benign. Not that there's much problem from health standpoints with R134 and other refrigerants, but regardless of what will happen or what will be discovered down the line, there will never be a refrigerant more benign, more environmentally friendly than air, and so as a result of that, we don't have to worry about leaks or anything like that, even in an application as delicate as aerospace. So that's a great advantage. Um, Comparing this to the SVCC, we have eliminated an entire evaporator, right, in order to produce the refrigerating effect. Since our cycle is effectively open, even though we're modeling it as a closed system cycle, we've eliminated the evaporator at the bottom. And so that means that's part of the simplified observation here. That means that we only have one heat exchangers instead of two. And so that means less bulk and, more importantly, less weight. So these systems, although are not small by any means, are significantly lighter than the equivalent SVCC system. For one thing, you don't have to carry that refrigerant either, so it makes for a much less heavy system, and that criteria is one of the key factors that's keeping it in the aerospace application. It's a very important design criteria, weight, in that industry, and so we've saved a lot of weight as a result of it. So significant advantages compared to SVCC in the air cycle machine, reverse Brayton cycle machine, and so, given that you don't see them around very much outside of aerospace applications, you probably are starting to wonder, well, this all sounds great. What are the disadvantages of this? Well, the disadvantage, there's only one really, but it's a significant one. And the disadvantage is that COP. And when you actually do some calculations, you find that the COP of the system that operates within the same temperature range as a SVCC is significantly lower for the air cycle machine. In the order of easily 4, 5, or 6 times less. And what that means is a cost in energy to produce a refrigerating effect. And so therefore, more often than not, that is found to be unacceptable for applications other than aerospace. And that's why you don't see widespread acceptance of these air cycle machines outside of that industry. However, as our conclusion of all this, if compressed air is readily available, and weight comes, let's say, at a large premium, then these systems are hard to beat. Air cycle machine, that's the name again of the refrigeration system that runs on a reversed Brayton cycle. Then the ACM cycle, the ACM system makes a lot of sense. Sense? Well, it doesn't cost as many cents, right? All right, let's end on this happy note, and I hope you have a good rest of your week. Take care, and I'll see you later.